So, the following is a discussion that I recently had on a flat Earth Discord server called Earth Awakenings with Tayler, who I don't know if she's a flat earther or not, but I've seen her hanging out at that Discord server, and I actually debated her once, like a year ago, more than a year ago, over on Modern Day Debate about abiogenesis. And as it turns out, Modern Day Debate reached out to me again recently asking if I would do another 2v2 debate again with Planet Peterson, which I had fun with the last time. This time against more well known opponents made by Jimbob, who I've spoken with before. And then he was going to be partnered with Tayler. And this was a decision by Modern Day Debate to pair them together, I think. Because then apparently, subsequent to that, Jimbob went on stream or otherwise mentioned that he did apparently not want to have a woman as his debate partner and he wanted to look for a different debate partner. So at this point, I actually don't know if that debate is going to happen or not, or if they're just going to do a 1v1 with Planet Peterson and Made by Jimbob about evolution. We'll figure out if he finds a partner for that. We'll see. But in the meantime, I thought, well, that was a really shitty. So Tayler and I basically decided to do a 1v1 because the last time we talked it was a 2v2 with Sal Cordova, and yeah, Tayler is actually like more intelligent than Sal or Jim Bob, like way more. I mean, Jim Bob is the lowest of all that rung. I mean, Sal actually does take courses in this, and Tayler says she's a PhD student in biology, like fourth year. I mean, she actually knows her biology. She works in like a cell bio lab. So in terms of the creationist that I normally talk to, she's on a bit more of a higher caliber in terms of her scientific knowledge about biology and cellular biology specifically. And she wanted to talk about abiogenesis. So this conversation gets pretty technical, it gets in the weeds. The one thing that I don't like is that Tayler has this habit of Googling studies like while we're talking and then claiming like, yeah, I know everything about the study. I've seen this study before. And like, I don't really like that. She did that in our last debate. She does that in this debate. But beyond that, I really do like talking with Tayler. She does ask good questions. It is actually a debate about the substance of the issue, and it's a good one until the flat earthers come in at the end for their Q&A, and I ended up staying there for way too long, and I cut that part out. So yeah, enjoy the rest of the debate. And on the subject of abiogenesis, yes, I am aware that James Tour recently made a video responding to me on the amyloid world hypothesis and going into several of the studies, and I am already crafting my response. Don't worry about that. It is coming soon. Just stay tuned on this channel and subscribe and hit the bell so that you stay notified when it comes out. I think that abiogenesis is the more likely explanation versus the alternatives for a couple of different reasons, right? So one, I hope that we could agree that we have life now and we used to have not have any life in the universe. Like, I guess we have very different worldviews on that. I have a naturalistic one. I believe you're a creationist. I don't want to mislabel you or anything, but we both agree that at some point there was no life and now there is life. I posit naturalistic hypotheses for that. You, I think, are trying to make the point that either a naturalistic hypothesis or explanation is either impossible or is inferior to a supernatural one, right? Do we agree that that's where we're both coming from?
So I just think the purely naturalistic and materialistic explanations are insufficient.
Okay. So the reason why I think that a naturalistic explanation is the more probable one is multifaceted, but I will say it's a lot of it comes down to the track record of naturalistic explanations over time. Like when we look at thousands of years ago, all of our explanations for all phenomenon were supernatural. It's like, get lightning because of Zeus, volcano erupted because of Pele, whatever. All of our explanations were supernatural. And then as time has gone on, more and more and more, we have figured out that the actual explanation was a naturalistic one through science. So if you're just betting on, overall the overall trajectory, it's a safe bet to think that most phenomenon will eventually have naturalistic explanations, given what we've observed overall with the history of science. So I would need a further justification if they're saying that, well, a naturalistic explanation would be insufficient for this particular field. I would need some sort of explanation for why this area is insufficient for naturalistic explanations versus all the other areas of phenomenon where we have found naturalistic explanations to be perfectly sufficient.
Right. I mean, it's just the fact that we don't find it sufficient, any of the explanations. And the more we learn about the cell, the more we're actually moving away from having that complete understanding. And yeah, understanding all the things that we need to be in play, and the more diversity and complexity we've learned about it, is kind of moving us away from that understanding. Whereas maybe in some other cases, the more we learn about the mechanisms of whatever phenomena we're trying to explain, the more we can understand how it might have happened naturalistically. Whereas I think whenever we peer into the cell, and all the experiments they've done to try to replicate it will show us that, in fact, we're not moving more towards of a concise answer as to how the cell came about.
So I would actually entirely disagree with your characterization that as we learn more and more about the cell, we're moving farther and farther away from having an explanation of the origin of life. I think that's actually completely reversed. I
Right.
don't know where you would get that characterization from, but I just 100% disagree with it. I mean, we're making progress
So,
in understanding more and more about the origins of life every year.
okay, so are you familiar with the history of the theory of abiogenesis?
Yeah, where they used to think, like when you're talking about the theory of abiogenesis, that's talking about spontaneous generation. That's not at all the same thing of talking about the hypotheses of abiogenesis we have today. Those are like
You
completely
know,
separate areas.
I mean, I'm not trying to interrogate you, but are you familiar with where the term came from and what we knew about the cell at that
Yes,
time?
that's what I just explained. Spontaneous generation was the big argument in the 1700s about
No,
abiogenic
I'm
origins of
talking about
life.
in 1870s. I'm talking about in
That is
18.
where it comes from, Taylor, though. When you're talking about, oh, they used to say that maggots would be spontaneously created in rotting meat, like that was where these abiogenic or like debates came from in the Enlightenment era.
Right, so let me tell you, I'm talking about in particular the term abiogenesis, not
Yes,
spontaneous generation. Like life
yes,
arising, like the beginning of life arising from non-living matter. So,
yes. Spontaneous
right,
generation, Taylor.
okay,
I mean that
right.
is
So
what that
there's a little
is
bit.
in the history of science. That is what you're talking about. That's where the abiogenesis, all that comes
Okay, well,
from.
let's
Was
just
that
go with
debate?
spontaneous generation for the sake of the argument. At this time, when they were saying that living matter can just arise, um, would you say that, we didn't really know much about the nature of the cell at that time?
Sure, yeah, and I would also say that that's the very farthest we've ever been from an explanation for abiogenesis. I would say that we are now closer than we ever were at that time. That's why I disagree with your characterization.
Do you think that there is some sort of hypothesis of abiogenesis that can explain the origins of life?
Currently, like in terms of a complete explanation and working mechanism, of course not.
Okay. So, do you think that over the years, since we've been researching abiogenesis, that we've found a lot of different issues with each hypothesis? Like you would agree with that, right? That as we
Mm,
learn more about the cell and as we peer into
yeah.
origin of life research, we're finding these different kind of issues arise, such
Yeah, I
as
mean, we find lots of problems in the fields of origin of life research, which is the case of literally every single field in every area of science where there's not a consensus theory. Every time in all areas of science, when there's not a consensus theory, there's a series of competing hypotheses, all of which are trying to tear down each other and trying to poke holes in each other. And whenever one arises where you can't poke holes in it, and it's reified by support, that's where it becomes a theory over decades. Like, we're not there yet in abiogenesis. That's not the only area of science where that is applicable. Like, you can talk about very well understood science like the Mpemba effect, where warm water freezes at a different rate than water that wasn't warm before. Even like you can compare everything. It is not currently known in our understanding of physics why that is, but it's a well-known characterized effect that we've known about for over 2,000 years. Now, we have absolutely no explanations for that, But we're not just going to throw out everything that we know about material science because we've been trying for thousands of years and still don't have a naturalistic explanation for the Mpemba effect.
Right. I mean, I see what you're saying in that, you know, we have these naturalistic explanations for things. We have these explanations for things in nature, whereas we used to think that they were some supernatural thing. But now, the more we learn about them, we know that there's some explanation, and that with abiogenesis, we're going to get there one day. So, am I representing your claim correctly?
Um, to an extent, I would even say that, like, not just we'll get there one day, it's like we are continuously making progress and learning more every single year.
Okay. So, do you think in the current state of the research right now, we can have any sort of understanding as to how life could have arisen by naturalistic means?
I think we can have some kind of understanding. When you ask a question like, can we have any kind of understanding? Yeah, of course, I think we can have some kind of understanding. Can we have anything resembling a complete understanding or a complete mechanism? No. We are definitely not at that level of sophistication yet. We don't have a theory of abiogenesis like that. But I do think
Right.
that, like, we can have some idea. Like, it's not like we're just totally lost.
Okay. Would you mind sharing how you feel or what theory you feel would explain the origin of life or what hypothesis, like, you know, because in my opinion, I think that there's issues with everyone. And I think that there's you know, abiogenesis has a lot of downfalls in terms of looking at a bottom up approach to it.
Mm,
I think yeah, so if you have a,
sure.
you know, a hypothesis that you think would be
Sure.
explanatory to the cell, I'd love to hear about it.
Okay, so I want to say that if I like, give you an answer for this, I'm not saying like this is the one that I think is correct. I can say, oh, here's my favorite of the different competing hypotheses, but that's not me saying like I think this one is true. And I'm like, I'm not saying that. Like if you would ask me what's my favorite explanation for quantum gravity, and I think that that would be analogous to where I could say, oh, well, energetic causal set theory. That might be my favorite explanation, but I'm not saying that is the correct one. There's lots of different explanations for quantum gravity, and we don't know which one is true. So, with that being said, my favorite of the different hypotheses for abiogenesis, there's RNA world, there's like iron sulfur clusters, there's metabolism first. Personally, my favorite one is called the amyloid world hypothesis, where you basically start with a type of protein structure called amyloids, which are sort of these self-replicating protein structures that can spontaneously form in the presence of like volcanic gases as catalysts, for example. So that one's my personal favorite. Again, I'm not saying that I think that this is definitely the way it happened. I'm just saying that there's a lot about this hypothesis that I personally find compelling, and I think it solves a lot of the problems that people commonly bring up about the origins of life.
Okay. Is there a particular like experiment or something that you'd want to share with the audience as to say, yeah, like this is a good indication that this can happen by naturalistic means?
Um, so there's a whole body of amyloid literature. It's not like just one experiment established this. There might be like
Okay.
review articles or something that compile a bunch, but overall, I think that it's just like the sum total of all the different properties and characteristic of amyloids that have been shown in the literature. Like you can find some studies that show that amyloids can self-replicate their sequence. And they can template their own sequence and replicate that in future generations of amyloids. There are other studies that can show that they can catalyze reactions that are important for metabolism. And there are other studies that show that they can actually select for the handedness of molecules, leading to
Okay.
like from a mixed state of right and left-handed molecules to just like more purely left-handed molecules. Like there are all these studies that show like this study shows it has this property, this study shows it has this characteristic. It's a body of literature, not just one particular experiment.
If there, I mean, so can you lay out some of these experiments or just some evidence? Because like, yeah, we can
Okay,
delve into like hypotheticals, right? But I really personally like looking at like primary literature, and that's kind of what I talked to you beforehand about like you know, anything that we're going to say is viable, we need to be able to demonstrate in some
sure.
manner, right?
So
So
it's like, what aspect of amyloids would you like for me to demonstrate? So, for
that,
example,
that
if
these
you're
can
if you're
come about, right?
doubting that they could form spontaneously in water with like a prebiotically relevant catalyst, I could point to a study by Greenwald et al. From 2016, where Basically, they formed spontaneously in water with different mixes of amino acids and just showed that amyloids can form spontaneously. Then, if you're going to
Right.
say, oh, well, I want to see that they can form with a mix of left and right handedness and then eventually lead to more like, enantioselectivity, then I would show you what I think a 2022 study. And basically like I think by route I can get the exact studies for you if you want, but I'm just showing like
I think I have it pulled
basically
up.
it depends on what characteristic of amyloid you would like to interrogate.
Okay, right. So, I would say first of all that we would need to like demonstrate that these self-replicating amyloids would be able to come about by purely inorganic compounds. Like,
Hmm.
I feel like that's plausible. That's just
Okay.
step one to
Okay.
me.
So
Like,
yeah,
that's
that would
very
be
minute.
Greenwald et al. That'd be Greenwald
Right.
et al. 2016. That would be showing that's showing like a prebiotically relevant catalyst with volcanic gases that is they're taking different mixtures of different amino acids and then they're showing that they come together spontaneously, naturally to form amyloids. And then there
Okay.
are other studies that characterize amyloids as being like
Here.
self-replicating, self-templating, catalyzing reactions, being selective for chiralities. There's all of these other studies for each one of these characteristics. There's not like one study that did everything.
Perfect. Okay, so that one that you're referencing about amyloids forming in water, just
Yeah,
from amino acids, was that one called Amyloid Aggregates Arise from Amino Acid Condensations Under Prebiotic Conditions by Jason Greenwald, Michael P. Freeman, and Roland Pike?
from
Right. Hold,
2016, right?
let me get it pulled up. I think that's what.
That sounds correct. That sounds right.
Yes, 2016.
Yep, that
So
sounds
I was
should be correct.
actually looking at this one earlier, and
Okay.
um, let's see. So, in one of their things that they mentioned in this paper was,
Yep.
well, first of all, from what I read, they were able to form what appeared as amyloids. They said it is worth noting that the polyalanine sample does not display an amyloid typical fiber diffraction as it lacks a Marindolial reflection at 47A. Most amyloid fibers give rise to a prominent reflection near 47A because the distance between the hydrogen bond strands in a beta sheet is constrained by geometry to be close to a 47A. So I think that what they were saying was it does resemble it. I did not find anywhere in here that it said that they were able to self-replicate them rather than take these amino
Yeah.
acids and form something that looks similar to an amyloid. And then
Yeah.
another thing they mentioned in this paper is that the polymerization reactions described thus far are not particularly representative of what would have occurred in a prebiotic soup, as they involve isolated amino acids. So these are some of their things
Hmm.
that they mentioned in this paper about how it might not, like they might be selectively favoring things to happen and then, you know, making, conclusions off of
So
it that, yeah,
So I was just
just
say
stretching a little bit.
the quote that you read was specifically for the polyalanine one that they did multiple different types of mixtures, and the one that was just all alanines was the one that had the atypical fold. They also did one with like all valine, that was just a typical stereotypical amyloid. They did one with a mix of like valine and I don't remember all the ones, but they did one with that was a mix of four different amino acids. Again, stereotypical characteristic amyloid fold. So like these things are amyloids. I've
Right.
spoken with
Yeah.
Jason Greenwald myself. Like he's told
Mhm.
me that they were forming amyloids in this experiment. Like then the second point was and I was trying to bring this up as saying that no one experiment is doing everything. I was bringing up this experiment as showing that this is showing the formation of amyloids spontaneously from just amino acid building blocks. And I can show you different experiments if you want to see the empirical characterization of their ability to self-template and self-replicate and all that stuff. That's like a different study. This is their study. This is about the formation of amyloids. Then you can have like I said, if you want to interrogate any particular characteristic of them, then I can show you studies about those characteristics. And
Yeah.
then your third point, sorry, you raised 3 points. I was trying to address them all. Your third point, I think, is the best one of the three in terms of the fact that they were creating this from basically like they were mixing in there were four different types of amino acids in one of them, but it is like four different isolated building blocks. They're not cross-linked to a bunch of other stuff. It's not like the just they're not throwing a complex mix of everything at the wall and seeing what will form. But I mean, they could do that. I mean, amyloids are ubiquitous enough to where you can form them from just a very crazy mix. I mean, the basically, given the right conditions, almost any protein sequence can form an amyloidogenic fold. Certain ones are more likely to form like than others, but they're like amyloid folds are so common that it really shouldn't be that surprising that you can form them like with just a random mix of amino acids, even
Right.
if it's not like completely pure. It's not impossible, but I would have to find another study that, if there has been a study trying that. I'm not aware of a study that's trying that, but like, if I had access to a lab, I would go do this one myself. I've seen a guy on YouTube actually who has done this experiment in his front yard of just he literally took the carbonyl sulfide, which is an incredible personal safety hazard, and he literally bubbled it into his own beaker with amino acids in it and was forming peptide bonds that way. So I've seen it done in a very ghetto way.
Yeah. Yeah, sorry for interrupting. I thought you were finished at some of those points, but that was a fair point that you
Uh,
brought up about that being alanine in particular. Um, but another question, just kind of to follow up off the first couple points I brought up about this paper, was they weren't self-replicating, right? They were just able to kind of take these amino acids and make them appear. They basically formed something that resembled an amyloid. Am I correct?
In this particular study, they did not even test whether they were self-replicating or not. All they did was
Right.
just confirm, yep, we created amyloids. That was the point of this study, was just to try to create them. They didn't try to do any sort of characterization of what kind of amyloids that they did create. They just said,
Mm.
oh, yep, we tested it. We did make amyloids. That's a positive result. So then they publish that. So then it's their future papers after this one where they start to characterize them, and then they show these self-replicating, self-templating behaviors.
Mhm. This is kind of a, I mean, as you would imagine, this is a problem that I have with some of these studies is that they're not really starting from prebiotic relevant conditions, just as they mention here in their own paper. Like it's not representative of what would occur in prebiotic soup, like having all these nice, pretty amino acids. It's not that surprising, as you stated, that they would form amyloids. And it's not that surprising that amyloids would make other proteins conform to their shape, because that's what happens in the cell. And that's what happens with like neurodegeneration. These amyloids will cause other proteins to start misfolding, right? So it's not that impressive. They're
I
kind of
would
taking,
clarify.
yeah, go ahead.
Sorry, I didn't mean to. But I would just clarify in this instance, it's not like the amyloids are like changing the conformations of other neighboring proteins like a prion does in prion diseases. That's not what's occurring in the templating. Basically, like they're templating the addition of amino acids on like a growing fibril of
Right.
amyloids.
You're right.
Like
Yeah.
basically, it just replicates the same sequence over and over. So it is a
Yeah.
sort of a replication of a sequence, but not a sequence of DNA, a sequence of amino
Yeah.
acids.
Of amino acids. You're exactly right on that point. So I was just gonna say, like, it's not that hard to believe, right, that this can happen. It's not that impressive to me, but what would be impressive is to show like these that they're doing something interesting like this from prebiotically relevant conditions, like just from inorganic molecules. As you would have seen, as you see, like through original life research, they kind of do everything in a stepwise synthesis. And as you were mentioning, in your interview with Jason Greenwald, he even mentioned some of like the housekeeping they need to do in some of these
Mhm.
experiments. I'm sure you would concede that. But so, as somebody just like just a spectator, just reading these papers, it's like, wow, they do have a lot of intervention going on and a lot of intelligent planning happening here. So it doesn't seem like these are really relevant for original life research, in my
So
opinion.
I think that overall, this is like an issue with sort of the approach to how research is done, right? Because the way that origin life of research is done is not trying to start from scratch and try to make life. Like that might be an intuitive approach, but like in the reality like of the grant proposal working in an institution, like basically you are trying to find a publishable result. And usually that involves making like a little niche contribution on one particular area. So you're not trying to like okay, let's start with scratch and let's make life in this perfect one pot experiment. Like, gone are the days of Miller Urey. The way that they're trying to, the way that they're thinking about papers is like, wow, like, I think that amyloids might be able to catalyze this reaction or something, right? And then if I show that they can do that, I could publish that result. So then for their experiment, that's all that they're interested. They have a very narrow scope of interest. So they're just going to like figure out what the cheapest, easiest way is that they can make some amyloids, and then see if those amyloids will catalyze just what they're interested in. They're not trying to start from scratch and do every step of the process. In like, I don't even think a single one of these experiments that I'm not aware of a single abiogenesis experiment in the last 70 years that has like gone with the approach of like, let's start with like the very most simple thing. Like they're all trying to show one particular aspect of abiogenesis. They're not trying to show the whole process in one experiment. So I think like your issue is basically just like their approach is not the approach that you want them to take. Like they're just trying to like elucidate, step 52 along the process or something like that, and you're wanting them to start with step 1. So like I understand the frustration because like obviously like I mean I really like origin of life research. I think it'd be amazing for them to do everything in one pot. I even brought this up when I was talking with Jason Greenwald. I was like, do you think that one day you will do the experiment where you do everything and like you start with only prebiotic stuff, you make the amyloids, then you let them go on with self-replication, and then you let them evolve via Darwinian evolution and see what you get at the end, like in like, massive experiment? And he basically was like, that would essentially be the culmination of my entire career. Like every single thing I've learned from every experiment over like the last 30 years would have to all be combined to do that. And like he's like that would be like a good goal for my lab one day to do, but he's like we're trying to like work on that, like work towards that by figuring out each little tiny piece of the equation along the way. So it's like, yeah, it's a big problem. I'm definitely not trying to give everybody the idea that the entire thing is solved from step 1 to life. But like, yeah, they are making progress in certain areas. We are characterizing amyloid like behaviors and activities and properties, and that's all just within like the last 10 or 15 years. Like that's all new stuff.
Right. So I wouldn't say they're not trying. Because I don't feel like they're publishing enough negative results in abiogenesis. And I actually think this is a problem with all like many different fields of biology and other types of research is people don't want to publish negative results. People want to publish what had a result. And so I think that there's a bias there as to say, they're not trying, they're just trying to do these individual steps. I would say that they're trying, but they're not able to because there might be some incompatibilities in the particular reactions or the like conditions for different
Mm.
parts of biopolymers to form, right? So different biopolymers would require different conditions in some cases. So I think to get them to like simultaneously have these reactions would pose an issue. And so I
Well,
would say that they are trying, but
I don't know. I mean, I asked Dr. Greenwald when I had him on the interview on my channel. I asked him if he tried it. I mean, it didn't. It seemed like he maybe had thought about it, but never like tried it and gotten a negative result and be like, oh dang. Like, so I don't know. Maybe I feel like he was being honest with me when he was describing to me. I was like, I was asking about such an experiment because I agree. I think that they'd be a great, really exciting an experiment. But to your point, like the reason why they're not doing that experiment is because it's a really difficult experiment to do. Like if they could, I'm sure they would. So like I understand what you're saying about, but I just don't know if like I don't know if anybody is actually attempting to do anything that you're talking about. I think that they're just like they think about it and they're thinking about, wow, like a 300 step synthesis of like, or like they're thinking about how complicated it is, and they're just like not even wanting to start it because it's like if you were the head of a lab, right? You have employees that you're responsible for. You're picking the direction that the lab goes. I don't think that anybody would choose to pursue something like that where you're like, it's so complicated. The results would take years to get. It's just like it's not a smart decision to like you want to try to pick away at certain things that you can make progress at. Like that's how science is typically done in every field, right? You say, I
yeah.
don't know about this huge research issue, but this tiny little area we can make some progress here. And like overall, like when lots of different labs are doing it, that's how the whole field progresses. So I do see that happening in the field of origin of life. research. Like we are making steady progress of like learning more and more every year, I think.
So, like in the Miller-Urey experiment, for example, like the amino acid production was only 2%. So, if we're going to
Mhm.
start and try to say, okay, we're going to try to get this like self-replicating amyloid from, purely inorganic compounds that we're mixing together, then we would have 98% junk. And that would be very difficult because, organic chemicals are very reactive. And so, they're going to react with whatever is in the environment that's, reactable. And if there's only a 2% output of amino acids, then why would they use that to like start the synthesis of like a self-replicating amyloid? That would
Yeah.
be very counterintuitive. And I argue it wouldn't be very effective. So I think
Yes.
like these are some of the real world issues with origin of life research. And, Jason Greenwald acknowledged that, like all the housekeeping they have to do
Mhm.
for these
So
reactions to happen.
specifically, we're going to talk about like amino acid production. I think we've come a long way since Miller-Urey. Like his synthesis pathways are no longer thought to be like the most prebiotically relevant. I think John Sutherland's lab has done a lot of good research on this about how you can not only get amino acids, you can get both amino acids and nucleobases starting from like cyanide chemistry. So you can start with a very simple molecule like hydrogen cyanide, and you can get to amino acids and nucleobases in a prebiotically relevant way. Like John Sutherland's lab has shown that just over the last few years. That's another one of those progresses in the field that we've made. Um, and in terms of the concentration involved, one, I would point out that the concentrations naturally found occurring on meteorites are in about the same ballpark as the ones used in that Greenwald 2016 study for amyloid formation, but also a study that just came out last year about the interface of underwater bubbles. Like basically, when you have hot volcanic gases from hydrothermal vents, and it's rising up in the bubbles, the interface between the bubble and the water that's evaporating actually causes amino acids to concentrate up to 30 times greater than the surrounding bulk. So that is a natural concentrating mechanism for these organic molecules right there at hydrothermal vents, which are already the most likely place for the origin of life. So you have a natural concentrating mechanism readily available for amino acids and nucleobases.
Right. So speaking of Sutherland, he actually had this really cool quote talking about the prebiotic synthesis of building blocks to which we have devoted so much of our time or only correspond to a small increase in the complexity of the system and to no increase in its aliveness. And he said this is a very humbling thought. And he acknowledges the lack of progress in the field, right? In the original life research. So he
I
like
really don't know if you want to necessarily like describe it like that, because I mean John Sutherland just in like 2023 or no 2024 last year came out with a whole like here's what I think about the current state in the fields in the field of abiogenesis. And like if I pulled up that quote, you wouldn't like it because he's pretty optimistic and about how we're closer than ever.
closer than ever, but not close at all, right? I think he would
Well,
admit that.
okay. Well, I can just, I mean, he talks about a future outlook. He
Yeah,
talks
if
about
you
where
want to
we
read it,
are,
go
and like
ahead.
he talks about his latest. Uh, I mean, he thinks that we're pretty dang close in terms of where compared to where we've been. I mean, he's pretty
Where do you
optimistic.
think that would be? How close do you think we are?
He says, okay, I'll just quote Sutherland. I think that the clues from experimental chemistry allow us to describe an ever more detailed geochemical scenario that drove multi step organic synthesis of building blocks destined to become biological on early Earth. I think that translation and the synthesis of loosely coated peptides comprising about half of the canonical amino acids must have been very early process. Recapitulation in the laboratory should one day allow us to create living systems from feedback molecules. So like yeah, you don't want to talk about John like Sutherland because he's not the guy that's saying that we're like completely clueless and he doesn't think that this is possible. Like Sutherland is one of the like cheerleaders of abiogenesis who thinks that
Isn't
yeah,
he still
we're closer than
working?
ever to getting this in a lab.
Right. So isn't he still working on like the synthesis of building blocks though of the cell?
So the latest two in that very thing that I was reading from his lab in 2024, the things that he had focused on as being his like biggest contributions recently. One was talking about that hydrogen cyanide synthesis of these building blocks, and then the other
Right.
was
So
The other big one was talking about um, sort of like an analog for very early tRNA before tRNA existed, and talking about the reason why we have the genetic code that we have today, and why we have tRNA in the shape that it is, and why the triplet codon pair, which is like really some exciting progress in that field. And also in amyloid research, they're also finding that amyloids preferentially bind with triplet codons. So that's another reason why there's three nucleobases per codon. Like you actually, we're finding out reasons why these things are the way they are in our genetic code because of the actual prebiotic chemistry. Like that's all super new and exciting stuff in the field.
Yeah. Okay. So Sutherland is still working on building blocks of life. And so his quote would still stand that the building blocks to which we have devoted so much of our time only correspond to a small increase in complexity and to no increase in its aliveness. So that point would still stand. We're still on the building block phase of how we would get RNA and proteins, functional proteins and RNA just from purely inorganic compounds. Do you
I
have
think the
any
other thing is
experiments
when you,
to show that that has happened?
I just, sorry, I was cutting you off. You can finish.
No, it's okay. I was just saying, do you have any experiments to show that we've gotten any sort of functional proteins or RNA just from inorganic compounds in a one pot, deal? Or something prebiotically relevant?
I'm not sure of any experiment that has sought out to do that as their goal. Like I can show you experiments showing, well, here's an experiment where they form amyloids from the building blocks in water prebiotically, and then I can show you here's experiments showing that amyloids have the catalytic abilities to act like enzymes like you're asking. But like those are two different experiments on the same stuff. They're both showing that amyloids can do this, but nobody's doing every single thing in one pot because again, the incentive structures for science and how it's done today are not aligned with that. The incentive structures is that if you do two things, you should publish two papers because that's better for your career. So anybody that both forms amyloids and then shows that they can catalyze reaction would publish two papers so they can get twice the output. So nobody's going to do that in just one pot, one experiment.
So you're conceding that there is no experiments, but you're saying that that's because it's by design and they're not trying to do it?
Yeah, I'm saying like this, the way that science is done structurally, like nobody's trying to do what you're asking because they're not incentivized to do so.
That's a strong statement. I don't think that represents the state of the research. I think that they would do it if they could. That would be really revolutionary, but I think that they're not able to find these results unless you can demonstrate otherwise because you're just assuming that they're not trying, you know?
No, remember,
Like,
I
that they
directly
are.
asked the researcher. I asked the guy who's publishing these studies, right? I asked Greenwald, who published the study of the formation and has published studies characterizing their self-catalytic, self-replicating ability. I asked him, why don't you do both of those in one study? I literally asked him this. I'm not assuming, and it's recorded his answer. He just said, well, we want to do it one step at a time rather than doing it all together. Like he gave the answer. Like I'm just telling you. Like I mean, maybe you could say that maybe you can find somebody that's trying this. I would love if you could show me somebody that's trying to do something like you're asking because I actually don't think that they are. I mean, origin of life research is already criminally underfunded. There are not that many people in the world doing this research. It is really hard to get a grant to do this research. And I don't think that anyone is trying to do the experiments that you're talking about because there's no money in it.
Okay, so yeah, is this the quote you're talking about when uh he was talking about how we like they ideally would like to. I'm just gonna go ahead and read this quote, okay? Because I don't want to like miss summarize him or whatever. I think in principle, yes. So you were asking about if amyloids and whether or not they could have chemical characteristics that would allow them to undergo something like Darwinian evolution. And he was like, yeah, in principle. And some of these missing experiments that we haven't been able to do yet because it's a bit tricky, is instead to start from our own pre-made amyloids and to do things like template themselves.
That
Um,
was not the part of the interview that I was talking about. It was when I asked him about, is it a future goal of your lab to do such an experiment?
okay, let me finish.
It was later on. But yeah, sorry. But that was
Okay.
relevant to what we're talking about. Still just
Mhm. And he said, we like to show what we'd like to show is that you start with something that has no amyloids, because then we will know that they will spontaneously form under certain conditions, and we will want to look at what formed and how it formed to say, did that involve some sort of selection,
Hmm.
where certain molecules got made much more than others, because not only were they more stable, but they were able to do it and to impose their own sequence on the rest of the pool. And that seems like we've shown mechanistically that could happen, but to show that it is happening is a bit difficult. So this is
Hmm.
kind of what I would say is like, showing that this stuff can happen is a bit difficult. And something else is like, just like I mentioned with the miliary experiment, like they get 2% of amino acids come out of it. So how relevant would that be? Like, how much do you think they could really do with that 2% in a bunch of tar, which is essentially what the miliary experiment
Okay,
made?
well,
So
Taylor, the miliary experiment was 70 years ago. I don't think it's relevant for this discussion really at all. The 2% number, especially not. So, I mean, like, you shouldn't just take the miliary 2% number and apply it to every biochemical experiment ever. We can move past miliary, like the efficiencies involved, we can go down to like each individual experiment. But the key part about specifically with amyloids or specifically self-replicators, and it's elucidated in these experiments, is that the end products need to be stable enough to prevent a back reaction. That is the case with amyloids. That's one of the reasons why they're so like looked into for this, is because over time, even if we were to just take your 2% value at like face value, right? If that 2% doesn't back translate, over time you'll have 100% product. If you just based on Le Chatelier's principle, like if you're not able to go back from the products, eventually the reaction will go all the way. So like again, it involves the very specifics of the chemistry we're talking about. In amyloids, the products are extremely stable. They don't go back. They don't hydrolyze readily in water. So you
right,
do get really good yields with amyloid formations.
right. So
Specifically, Greenwald showed you can form amyloid spontaneously, and then in a different experiment, he showed that amyloids can have these self-replicating factors. What he's saying in the quote you just had about why it's so difficult, like think about what you would have to do to characterize Darwinian evolution in one pot. Like, think about that. Like, how would you actually get the sequences for all these amino acids? Like, are you doing a mass spec? I mean, like, it's a logistical nightmare in terms of trying to like figure out the design of the experiment to show here are all the generations of amyloids that are changing, like, and to sequence each one of those. I mean, I don't know logistically like how you would actually do that in a lab. I think that that's what he's referring to in terms of the difficulties of showing something like this. But he did say that his experiments do show that all the properties required for Darwinian evolution are present in amyloids. Like his experiments have shown that much, at least.
Real quick,
okay,
on a
so
point of moderation, guys, would you
yeah.
rather we put in a clock where things like, I don't know, we go for 1 minute at a time or maybe 2 minutes at a time? That way it's not just, one person going for an elongated period of time.
Sure.
Yeah, that would be good. That's fine.
Would
Yeah,
you
I
guys
try to keep
prefer
my
that
points
or do you
here.
want to keep it the way it is currently?
No, I think that would be a good idea because I try to be like really concise so we can cover more material in a short time. But yeah, that'd be cool. Let's see. So I did want to mention, like, are there any other experiments where you think that they can form, amino acids that doesn't have many byproducts that would mess up future reactions?
But I mean, we like the ones we've already been talking about have shown that. I mean, like amyloid formation in general
I'm
proceeds
talking about the formation
spontaneously.
of amino acids they're already planting into these amyloid experiments.
You mean the formation of the amino acids themselves? Okay, I would point to John Sutherland's like lab of like creating both amino acids and nucleobases from like hydrogen cyanide. I would
Right,
point
and
to those
you and Jason Greenwald actually mentioned that, and he said that they were not necessarily formed in the same condition, but I don't know if we didn't talk about, or y'all didn't talk about how many byproducts were formed. So that might be something cool that we could figure out is like how many byproducts are formed from these reactions, because we know that they're doing stepwise synthesis, because in a lot of cases they do have a lot of byproducts formed that would mess up subsequent reactions.
guys. Yeah, I mean, I kind of feel like overall the state of the field has moved kind of past the formation of building blocks, considering the fact that like we find amino acids naturally occurring on meteorites. Like it seems readily obvious that there are natural processes that are creating these things, like out in space at least. I mean, it's not, at this point, I mean, back in the 50s, it was argued about like whether or not it was possible for the building blocks themselves to form. But at this point, it's pretty established that at least the building blocks for, in terms of lipids are naturally occurring, amino acids are naturally occurring, you know, I mean, you have the building blocks of life being occurring. It's just how those combine to get the first proto life. That's the big question.
Yeah, that is a big question. And so even on the meteorites, like there would be a lot of other junk that's around it, right? So it's not just like these pure isolated forms that they're using for these
Hmm.
experiments.
Yeah. But again, I think you might be surprised just how ubiquitous amyloid formation is. Like,
No, I agree. I agree that amyloid formation definitely has some cool, things to offer. And that they can temp with themselves and cause other amino acids to come into certain conformation. That's really cool, and I agree with you on that point. But I think that all of these experiments are really fine-tuned to give these results, and they would even acknowledge that. So it's not that prebiotic irrelevant. It is cool that they do that, but getting there from inorganic materials is another story.
so I think that there's a bit of a fallacious reasoning in saying that just because the experiments are, fine-tuned by the scientists, that means that they can't occur naturally. Like, for example, if I was designing an experiment to create snowflakes, I might have to fine-tune the conditions for that. Like, it can't just occur in room temperature. I'm gonna have to go specific temperature, specific pressure, specific moisture levels. Like, I'm gonna have to fine-tune that experiment to form snowflakes in a lab. But that
So
doesn't mean that therefore snowflakes don't form naturally. That I just don't see
I'm
why.
not I'm not
The
necessarily
fact
saying
that
that,
you
but
have to
what
uh,
right.
okay,
Can you tell me what fallacy I was committing
yeah,
by saying
I'm saying that the reasoning is fallacious in that it's not just because you have to design an experiment in certain conditions. That doesn't mean that those conditions are improbable. That's what
no,
I'm
but it
saying
is
is a fallacious like jump in logic.
right. So, but it would mean that this would not be relevant as to give evidence for undirected original life research. And
No,
so, and to say
I
that it
don't agree with
does,
that at all.
let me let me finish really quick. Okay, so to say that it does give evidence for undirected abiogenesis would be like special pleading in a way, in my opinion, because you're deliberately ignoring aspects that are unfavorable to the position, and
No, but I'm not saying that
deliberately
either.
ignoring.
I'm not saying either one, Taylor. I'm really not saying either one. I'm not saying that this gives evidence for it, and I'm not saying that it's evidence against it. Like, I don't think it's either one. That's my point. Is that I'm saying
Okay,
that you can't generalize based on like the fact that scientists have to use special conditions in the lab to get a certain result. You cannot then generalize that to say that means that in nature it's either probable or improbable. I just don't think it's related.
Unfortunately,
okay.
I'm gonna
So
have to step in again, guys. It's gonna have to go one at a time. If we're constantly interrupting each other, it's just audio chaos. Let someone finish getting their point across. When they finish speaking, maybe do one Mississippi, two Mississippi, and then carry on. Probably a better way to go about the back and forth. Sorry to interrupt again, guys. Go ahead.
no, I'm sorry if I did that, Galtrax. But you can finish if you're talking.
No, I'm good. I really didn't know that we were interrupting each other.
Cool. So what I'm saying though with these experiments is that those don't provide a good case for this happening in undirected abiogenesis, which is what I'm saying. That I don't believe has happened, right? I don't think that the evidence shows that undirected abiogenesis is sufficient to explain original life. And I think that, the research that you're bringing up is very compelling in that amyloids can exhibit these properties. And I would agree with that. That is very interesting. But I don't think that the experiments that you've mentioned would give evidence to undirected abiogenesis and original life. If you have any other evidence that does support undirected original life, I would love to see it.
So I think that we need to drill down a little bit more on what you're expecting for what you're asking for evidence for unsupported abiogenesis, because the experiments that I'm showing are that you can have like self assembly of these kinds of structures that we have seen have very interesting chemical properties relevant for life. So you're pointing out the fact that yes, but those structures only self-assemble under certain conditions. And so you're saying that you don't count this to be evidence that would support that this could happen in an undirected way. But I think that the crucial piece that we're missing here is it would be evidence if those conditions that the scientists are creating are prebiotically relevant, right? Would you agree with that? That's a big if, but I'm saying if the conditions of the experiment were prebiotically relevant, then would you consider it to be supportive evidence?
Yes, that would be a small step forward into the original life problem. But
Okay.
I would agree, and I would concede if they were prebiotically relevant, like if we could get these amyloids to cause these self-replication just from prebiotically relevant conditions, that would be very peculiar, and I would consider that as evidence on your part.
Okay. So basically, we need to show the experiments are being prebiotically relevant. So I've seen things like certain volcanic gases can catalyze the formation of these amyloids. That's a prebiotically relevant catalyst, like carbonyl sulfide would be a volcanic gas bubbling out of such a prebiotic earth. So that is at least showing you can get amyloids to form with a prebiotic catalyst. And then the experiments that show that amyloids can form with a mix of left-handed and right-handed amino acids. I mean, are we not making progress in showing that there are prebiotic conditions that would facilitate amyloid formation? I mean, what exactly is missing that you still haven't seen?
So what you were just mentioning with the volcanic gases was kind of what we talked about earlier, and even in that paper, they mentioned how this polymerization reaction described is not particularly representative of what would occur in a prebiotic soup because they involve isolated amino acids. So even in that experiment, they even acknowledge that this isn't prebiotically relevant.
So then, if they had done the experiment where they had more variety and it just had a total mixed bag of amino acids, or like if they just replicated the kinds of amino acid that are found on meteorites, would you then I mean, is that what you would prefer? I mean, what I mean, I don't know because like we could do those experiments. I mean, I could do that experiment if you wanted me to, and we could just show amyloids can form that way.
Well, you'd have yeah, that'd be a wonderful experiment if you could do it. That would be one step forward. But what I'm saying is, even with that, right? So we're assuming the amino acids are there. And so, if you want to say, oh, well, the amino acids came from a meteorite, then I would say, okay, well, let's take a meteorite sample and try to make this thing happen. Or, if they're saying they happen from the Miller-Urey experiments or from the John Sutherland experiments, we would need to take those conditions and add them in with the conditions of forming these amyloids and, having them self-replicate, things of that
So it
nature.
it does just kind of sound like you disagree with the overall approach of the field, like because what you're wanting to see is like literally for them to basically do a sort of updated Miller-Urey experiment where they're like starting from scratch and then you want to just see how far along the trajectory towards life they can get. And again, like that is just not the approach that anyone's taking. Nobody's that's not the approach to the field. Like again, the approach is just small, like I'm figuring out step 32, I'm figuring out step 51 over here, like everyone's siloed working on their own little particularly slice or niches, and like that is how progress is made. That's not something that's particular to just the origins of life. That's every field of science works that way. Like
Right. So
nobody's
there are
trying to do
experiments
everything
like,
all at once.
right. So like I would disagree that they're not trying to do that. I think that they have been trying to do that. But like, for example, with the experiments where they're making amino acids from inorganic compounds, they tend to have a lot of garbage and junk formed with it that would be, you know, possibly a hindrance to further steps. So I think that they probably have definitely tried it, but it's just based on the nature of how it's forming would not be optimal for anything because they have to do this housekeeping, as Jason Greenwald says.
Yeah, well, I do think that it is optimal because again, the kinematics do favor the formations of these stable compounds that don't backslide. We already went over this subject, but you can see very favorable formation of biologically relevant products in prebiotic reactions. Like Like
But did
again, the
they do it
chemo
with
is favored
Tyler?
if the stability works out to favor the products, which is the case for amyloids. You can get very good yields.
But in the amyloid experiments, they were using pure amino acids. They weren't using a bunch of tar residue that would have happened from lightning striking a soup or whatever. Like they weren't
I mean,
using
well,
these
we do
conditions.
find pure amino acids. I'm sorry, I didn't mean to cut you off on that one. I thought you were
No, it's
done.
okay. I was just saying, like, you know, to make amino acids, the intricacies of what would have had to happen in those reactions would cause a lot of other byproducts. And so let's start with that, right? And then move forward with but they even admit in your amyloid papers that they're using pure amino acids. So that's already kind of a bias. And then we haven't even got to step one. Like, so we can talk about what would come after that, but we're still see how like there's so much intricacy just in the first three steps.
Okay, Taylor, I gotta push back into thinking that, oh, they use pure amino acids, therefore it's a bias. Like that is a logistical thing. Like you wouldn't be able to do the experiment if you're just throwing a bunch of messy chemicals. Like you wouldn't be able to characterize your results. Like you cannot do lab work in the way that you're expecting for origin of life research to work. Like your expectations for the field are impossible. They're not realistic because like just think about what that involves. Like you've worked in a lab, right? Think about how you would characterize your reactants and products for such a you couldn't. You literally could not. If they were doing it the way that you did or like that you want them to, like you just like you literally couldn't do anything. It's too complex. You can't characterize your results.
So if you think that it wouldn't be realistic in a lab, why do you think it would be realistic in nature, which is even more messy?
Because in a lab, you can learn things about nature by simplifying it down to where you can then have a controlled variable setting to where you can get right down to establishing causality by only having one variable of manipulation. This is how all science works. Every single science experiment takes the real world, which is really complicated, tons of variables, and they try to control as many variables as possible to get it down to just one independent variable that they're manipulating. That's the very principle behind all of science. This is nothing new. This is nothing special to origin of life.
So I would agree. You want to isolate as many variables as you have to look for a particular chemical reaction to occur. Like, can this happen logistically just based on if we have this and this, can we form this, right? And so you want to isolate those variables. So I totally agree with you on that point. But what I'm saying is that we could not then apply this as to what could have happened in prebiotic Earth.
No, you can. That's what I'm trying to like have you understand here. Like if I'm interested in, okay, I've got chemical A and chemical B. I want to see how they interact with each other. So I make a beaker with chemical A and chemical B in it, and then I analyze that beaker. Now, in real life, say that chemical A and chemical B are just one of 200 chemicals that are naturally occurring in this pond. But in the pond, we know that eventually chemical A and chemical B will meet and they will interact in the same way that they will in that beaker. So you isolate the variables, you reduce it down to just what you're interested in focusing in. You characterize that in your experiment, and then you say, well, that's what's going on in the much more complicated version that I can't characterize in a lab, realistically speaking. That's like every science experiment relies on doing that.
So are you familiar with special pleading,
Yes.
the fallacy? Okay, can you
Yes.
tell me what your definition of that is?
Yeah, special pleading would be to say, oh, well, in every other scenario, I uphold this rule, but in my particular scenario over here, it doesn't apply.
So, yeah, so I would say that it's an argument which someone deliberately ignores aspects that are unfavorable to their point of view. So,
You
to
would
say
say
that,
that? It
yeah,
sounds like you were reading from something.
would you say? Sorry.
Would you say that? Because it sounded like you were reading from something.
Yeah, no, I would just want to have like a real definition so I didn't
Okay.
get it wrong because I don't want to like have a false definition. So, yes, I did read it because I don't want to, mess it up. So,
So why
I
ask me if you have it written in front of you?
because I want to know because I want to ask you based on your definition if you think
Okay.
that's what you're doing. And if we can't agree on definitions, then we can't
Sure.
come to that conclusion. So,
Well,
I think that
I pre-ran this 2 times already with you by saying specifically this is the case for all fields of science, not just origin of life, because I thought you might accuse me of special pleading, so I wanted to be very clear with my words that that's not what I'm doing because every field of science does the same thing. This is not something special to origin of life research. I was very clear about that.
right. So what I'm saying is that in nature, you're not going to have these nice chemical compounds. So if we're trying to isolate a particular reaction, yes, we'll try to take off everything else that could mess up the result. But then, so we can say from your experiments, we can say yes, amino acids can come and form something that looks like aggregates. And then another experiment say yes, if we give it a template for an amyloid, then we can see it impose a sequence on others. So we can make those claims. But what we can't do is say that would happen and would be relevant in prebiotic Earth. That's what I'm saying.
But the template in those amyloid, the amyloid self-replicating template is not all that improbable to have formed naturally. Like, it's basically like you can form these naturally, you could characterize what kind of amyloids are forming naturally, what kind of sequences they would have, and then given enough of that, you can calculate, oh, well, here's how many years it would take to form a sequence that is a viable template. Have you done that math? I mean, it's like
Right. So
the total sequence space versus the total sequence space of suitable templates is not that infeasible for the kind of timescales that we're talking about here of like a couple million of years.
So, I mean, didn't you ask Jason Greenwald a similar question? And then he responded to say that even a short peptide of 100 amino acids would have so many possibilities that mathematicians can't even fathom how big the number is. So he's acknowledging like the chances of getting like a particular sequence just from
Yes,
pure amino acids is so incredibly low. So to say
exactly. No,
it's
no.
likely wouldn't, in my opinion.
Oh yeah, yeah. That is true for the case where you're only interested in one particular sequence, which is the fallacy of most creationists when they talk about abiogenesis, because we're not interested in just one particular sequence. The sequences that can act as templates for amyloids are degenerate. There are many different sequences that can act as viable templates, and so therefore the numerator is a lot bigger number than just one over the total sequence space. So the actual probability is much higher than what you just laid out.
So what would the actual probability be?
So you'd have to go in and calculate out of the total amount of sequence space for the total amino acid residues that you're interested in, how many of those can act as suitable templates. So that's a pretty huge number given that there's like roughly like half or more of the amino acids have a predisposition towards forming amyloidogenic sequences. The qualifications for the template are basically just have to be like, I don't know what the bare minimum is, but between like 5 and 8 amino acids long, and yeah, you just have to like have two of them that are kind of mismatched come together with a little bit of an overhang, then boom, you have it coming. So like that is going to happen if you have enough like short peptides. I mean, that's basically a mathematical certainty of one.
Of one?
Yeah, all you
So
need
you're
are
saying
like two mismatched. You need two mismatched like peptide fragments of like pretty short fragments that relatively form like or that form pretty frequently whenever you have these catalysts like these volcanic gases. As long as they come together, which is basically guaranteed to happen, it can act as a templated like self-replication of that sequence. So I don't know. I mean, I wouldn't be able to go with the exact numbers and give you exact numbers because I don't know what the numerator of that equation is versus the denominator, but I like those odds. I would take those odds.
odds of one?
I would take those odds.
One in
It's an,
what?
it's an odds of one over a certain long enough period of time, given a certain volume. We haven't done any of the specifications that would be necessary to actually do these numbers.
Okay.
Like you would need to
So
specify time, volume, concentration, all kinds of things in order for us to actually calculate this, which I don't think we're gonna do over a live debate.
I got you. Yeah, well then I would just kind of be a little hesitant to say it's probable to happen, but even with that, even giving you that, yeah, we have like that these, the odds of it making an amyloid, are high. Like we haven't even really scratched the surface. So one more point I want to make before we can move on, if it's okay with you, is that even in these cases, they're assuming these pure or these available nucleotides of the right orientation that are just ready to react, and that's making a big assumption in prebiotic Earth.
No, I don't think that it is because we do find amino acids in individual like amino acid form in residues on meteorites that were you to then pass that naturally volcanic gas over them in an aqueous solution, they would form a peptide bond. It's that's all prebiotically relevant. You don't have to do any kind of like intelligent activation or anything behind that. That's all naturally occurring.
Have they used, just out of curiosity, have they used the amino acids from meteorites to make the polypeptide bonds?
Nope, that would be way too expensive. I mean, I don't
Okay.
know
And
if
then,
you know
like,
how much it
what is the
costs.
concentration?
The
Sorry, what is the
concentration that they used in that Greenwald et al. Study is roughly in the same ballpark. At least last time I looked this up, it was roughly in the same ballpark as the amino acid concentration found in the Murchison meteorite. I don't know exactly for Bennu, the latest sample, but if you're just talking about how expensive per gram those amino acids are, I mean, you would have to be a crazy person to use those amino acids as the feedstock for your experiment. Or at least you'd have to
I'm just
have like
wondering if,
money to burn.
right. I'm just wondering on early Earth, like how many, because we're just like kind of assuming there's there and available and ready to form. But like what's the highest concentration we found in nature without any
Well,
contamination that we
right, I
found in
did.
some of
I
the
did
meteorites?
previously bring up the that hydrothermal vents at the interface of those hot gases and the water. They concentrate organic material and like amino acids and nucleobases up to 30 times higher than the surrounding bulk. So there are concentrating mechanisms that are prebiotically relevant and natural. But we can move on at this point.
Yeah, I would be skeptical, like in some of the meteorite things about contamination that they found to be at play. But even then, all my other points still stand. We are
About the contamination, they just sampled it from Bennu directly from space. So there's no opportunity for contamination at all. That thing never came into contact with like Earth. They took it directly from the space and then had it in a sealed, contained environment. There was no contamination, and they found, I think, 14 out of the 20 amino acids.
in what concentration and orientation?
I don't have those numbers for you at the moment,
It's
but
okay.
I mean, I can send you a link
Yeah.
to the Bennu publications so we can see what concentration they're at. But again, the concentrations can be increased at hydrothermal vents. We know the mechanism that does that.
Were you trying to take a break or were you trying to? I'm sorry, I
No,
didn't
I
know what
mean,
you
I
meant by
thought that
that.
you were trying to. Oh, no, that was me. Just I had something to say and I didn't want to interrupt you.
Oh, okay, gotcha. So, like, just assuming, I just have a couple more questions because, like, I think that we're not like we're still on such an early phase of this question about how to like form. Like, we're still trying to figure out just like the first, like,
Sure, yeah.
self-replicating biopolymer. Like, there's so much more to go. And
We
I was
agree
just
on
gonna
that.
ask, do you really think that there's other experiments that use prebiotically relevant conditions that actually prove undirected original life synthesis? Because
Like
the millimeter
prove
array would be a good
undirected origin
experiment.
of life synthesis. Well, yeah, of course not. If somebody could prove undirected origin of life synthesis, then like we would have a theory of abiogenesis. But again, we
Right.
don't. So like I think that there are, again, I'm not saying that there's any one that has all the answers every step along the process, but I do think that there's lots of exciting like studies that are showing like certain individual pieces of the puzzle. I'm not,
Right.
each and every
I
study
agree.
doesn't start with the very beginning of the puzzle piece. They're just adding a little bit of extra pieces, connecting little pieces together and things like that. Like, I mean, there's like a lot of, just in the 2020s, I think there was some really interesting work on like prebiotic phosphorylations and how that can occur. There's some interesting work on protocells and like the area that I'm most interested in for the future is looking at like protein nucleobase chimeras. And like where you
Mhm.
have a protein and some sort of nucleobase together in one kind of molecule, and then like seeing what kinds of properties those molecules have. Um, those are ones that like are really exciting to me for
Yeah.
like future prospects.
And I think that like even in the origin life research, that gives evidence like the amount of manipulation and like standardization they need to have for these experiments gives me evidence that they do have some sort of interplay here in the original life. Like if they were able to just kind of leave it to its own devices, like what would really come from it? So I think the amount of intervention in these experiments, like, don't, at least they don't point to undirected abiogenesis. If not, they point to the contrary, which is some sort of intervention at the origin of life.
I mean, I just bring up the example again. Like, if we were to form snowflakes in a lab, that doesn't, we should not then conclude that you need intelligence to form snowflakes. Like,
Mhm.
we just have to understand that in a lab, no matter what the scientist is studying, no matter if it is undirected, doesn't need intelligence, or if it is required intelligence process, both examples require the scientist to design the experiment. So the fact that the scientists had to design the specific conditions of the experiment does not allow us to say one way or the other if the process itself that they're examining is undirected or requires intelligence. Like, we just cannot conclude that from the fact that it had to be designed by a scientist in the lab.
And intervention every step of the way, like intervention in many cases, like removing the bad parts, right? To then go on to the next step of the reaction. Any sort of intervention like this really shows the need for some sort of just the lack of ability for it to happen on its own.
Again, I don't think that that is what this is showing. Like, there are tons of reactions that are done in like synthetic like labs that are also reactions that occur naturally, but in the lab, when they're studying it, they have to do exactly what you're saying. They have to intervene in the experiment so that they can do it logistically in their laboratory. Like, it's just like, no matter what you're studying, this is just a thing like with that's inherent to all laboratory experiments of any kind.
Mhm. I just think that it would be wise to acknowledge, like in the paper that you referenced, they just said that the building blocks weren't selected for prebiotic relevance. So I just don't think in those experiments we would even be able to apply them to original life research if they're not
Like,
prebiotically relevant.
the reason why you can use like building blocks or something that's not prebiotically relevant in an experiment about looking for something in abiogenesis is that that's not the part of the experiment that you're interested in. You acknowledge, like, if you've ever done science, that you have one particular area of research interest that you want to know. You want to know, can this chemical do this thing? And then, like, you're not interested in, oh, well, let's just see if we can do the entire step from step 0 to the step that we're interested in a prebiotic manner, because that's not relevant. That's a waste of time and resources for your lab. You're only interested in, you're only going to be publishing about the one particular thing that you're trying to study. So you're just going to skip all the other steps to go right to the step that you're interested in. That's in reality how all of these experiments work. So, like, I don't think it's a fair criticism to say, oh, well, they can't have any kind of conclusion or they didn't learn anything relevant to abiogenesis if they started with, they started with the designed molecules and then showed, hey, there's this really cool, interesting prebiotic chemistry that can come from this. But, if you started with designed molecules, then therefore that invalidates the findings of their studies. Like, I don't think that logically follows.
Yeah. So unless they can show that like whatever precursors they're using could also be there in that concentration, I don't know why you wouldn't acknowledge that that wouldn't be a fair representation of
Because you're not understanding what their goals, what the
I
motivations
do
of the
understand their
experiment
goals.
are.
I'm just
So
saying.
let me give an example,
Yeah.
right? Because I sent you one of these studies, right? We just talked about the chimeras between proteins and nucleobases, right? That is a study that did not start with like prebiotically relevant starting blocks, right? The point of the study was not to say, here is what happened before life existed. Our molecules that we created in our lab are the intermediates in abiogenesis. That's not ever what they were trying to do. The point of their experiment was to like investigate what kind of properties these chimeras that they can create have. They're trying to say like, well, like what can these things do? They're not even trying to say these have to be the abiogenesis self-replicators. They're just investigating what properties these chemical systems can have and whether or not those properties could be relevant in a setting of abiogenesis. Like in this kind of early setting, if these molecules have been there, what could they have done? And then it's like, from there, if they find interesting results, then you do further research and saying, okay, well, can we get molecules that are doing similar things with prebiotically relevant building blocks? Then you can go and do all these further investigations. Like, these are all just multiple different studies. You want them all to just be in the same study, perfect from the very beginning. And I just don't think that that's realistic to expect in like literally any field of science.
Hey guys, I just wanted to step in real quick. We're about an hour and 10 minutes in. You guys said you wanted to go a little over an hour. Do you guys want to keep going? Do you like the flow of everything, or do you want to switch to like Q&A? What are you thinking?
I mean,
Should we
I'm happy to
continue where
do
you're at?
I'm happy to
It's
do
up to you
Q&A,
guys.
whatever. I mean, Taylor, what are you feeling?
Yeah, I was just gonna ask him one more question if that's okay. And then
Sure.
we'll do Q&A in like 5 or 10 minutes. Is that okay,
Sounds good.
Galjax?
Yeah, sounds good. Just
Okay.
whatever works for you guys. Just making sure
Yeah.
that,
So
you don't lose track of time or whatever. All right, carry on.
so I know that you're one of the more optimistic people that like origin life research, and I think the person that you were interviewing also told you that, Dr. Greenwald. So I want to hear your rundown of original life in terms of like where, the genetic material came from, where did the RNA come from, in what conditions did it form, like what conditions did the amyloids form, like where did they form, and then how did we get, to life from there, if you can give me a rundown of your.
Okay, yeah, just an easy question for the end then. Just give an overview of the entire origin of life. Okay. Also, I think Dr. Greenwald was saying that his partner, Dr. Riek, was really an optimist about abiogenesis research and that he
What's
was more
his theory?
of a pessimist or whatever.
Hmm.
But yeah, interesting combo. Um, but yes, so in terms of the way that, if I'm trying to think about what I think is the most probable given the information that we have now, right? And again, with the disclaimer, speculation on my part, of course, there is no theory of abiogenesis. So I would say that for the building blocks, again, I like Sutherland's reaction from starting from simple, like organic molecules like hydrogen cyanide, getting nucleobases, getting amino acids. I think that it's likely for protein chemistry and for maybe a lot of the sequence information to have started in proteins, like in amyloids, because we do see amyloids forming with just the sequences of whatever amino acids are present in the environment. And then from there, you have a population of different amyloids that all have slightly different sequences depending on just the exact circumstances of their formation. That gives you a population with variation in fitness because in this situation fitness is molecular stability and the stability of amyloids is going to vary based on whether like their actual sequence composition. So you have all the steps then for Darwinian evolution, right? For you have a population with a variation in fitness effects. These amyloids are continuously growing, like according to these fibrils, right? And they act as templated information. We have the studies showing that they can act as templates for their own self autocatalysis, and that gives you a certain form of heredity. And we have seen also that study I was showing you with the RNA nucleobase chimera shows it actually characterizes the fidelity of the replication of the protein sequence. And you can actually see the mutation rate in just these protein sequences. Then you have the interaction between these early amyloid proteins together with lipids and nucleobases and like early, adenosine and things like that. To where we have characterized that in the lab too, where amyloids will regularly adhere to lipid membranes and form these little protocells that are really interesting. Then, like they'll associate preferentially onto the lipid surface, exactly like protein, like lipid proteins, membrane proteins today. You also have amyloids interacting with nucleobases in a way that prefers the triplet like codon type pairings. You've got a really bunch of really interesting interactions there. So yeah, I think that when you combine these different building blocks, the proteins, the nucleobases, and lipids together, you're getting these first protocells, which can take advantage of the surrounding environment of a hydrothermal vent, where you have a naturally occurring proton gradient, which is what
So
life
let's stop
uses
there
for
'cause
itself.
it's getting a bit long. Like I
Well,
wanted to
Taylor,
have like a little bit of a back and forth before we ended, and we gotta shorten it a bit.
I know, but you literally asked me to summarize the entire origin of life as your final question. It's like I don't know how to do it, more concise
Right.
way. You asked for literally just explain everything at the end.
Right. No, I got you. I meant like where did it happen, like a hydrothermal vent or a
Yeah.
soup or
Well, then just ask
in
me a more concise question. Don't ask me an open-ended question if you don't want if you want a concise answer.
Okay. So I'm just wondering, do you think that the prebiotic, like the molecules, the like RNA and the proteins, that this happened in a soup or a hydrothermal vent? I'm just kind of curious.
Well, it's an aqueous solution around hydrothermal vents. I don't know what you mean by soup. It's not really
I
a
think John
scientific.
Sutherland's
Soup is not a
John
scientific term.
in John Sutherland's research, he was not invoking hydrothermal vents. For different reasons. And so this is like kind of like some of the incompatibilities and the locations that these things would have happened. And then so like you kind of mentioned hydrothermal vents, but John Sutherland wouldn't have worked. I think it's for pH and temperature reasons that wouldn't have happened. So I just want to point out some of these incompatibilities just from like basic molecules. Just trying to get these basic molecules down, there's already
That's not an
problems. Like
incompatibility, though.
so, what would the pH have had to be for your amyloids to form? Or
Right.
for
Well, amyloids can form at a vast number of different pHs and can be catalyzed by surrounding lipids. For example, there are amyloids that only form at extremely high pHs that will then form at neutral pH when they're associated with lipids. So it depends on the chemical environment, and lipids are naturally occurring at hydrothermal vents. So your question is a little bit too vague to give a good answer to, because like it's too open-ended, that you haven't specified enough conditions to give like one specific numerical answer. But the reason why it's not a contradiction is because many of the compounds found naturally around hydrothermal vents are not formed at those hydrothermal vents. Things can dissolve in water and disperse elsewhere. That is very common in the ocean. And yeah, there are also multiple different synthetic pathways to get to amino acids. Like John Sutherland's is one that I like, but it's not the only one. And we know that amino acids are naturally occurring like in nature. So
right. It's also interesting how he used things like UV light or these like I think in one
yeah.
of his experiments he invoked like a meteorite crash to like have the energy to bind these RNAs together. It's so funny. Like all the different environments and conditions just for each of these to form like um and how they have to form in these different conditions. So if you were to get them to form from inorganic compounds, just the nucleotides and amino acids from scratch, like in the same,
Hmm.
conditions and scenarios, that would be a little bit more impressive to me.
I
But
would
I don't
say
think any of the research right now is very compelling for like undirected inorganic compounds to undirectly become like some sort of like biopolymer that's usable.
so. The majority of all carbon that exists in the universe is in the form of very complex organic molecules that are created naturally in space on ice by ultraviolet radiation. Like this is like astrophotochemistry. Like very commonly creates very complicated organic molecules, including like the nucleobases. Like we literally, they are naturally occurring in meteorites at appreciable concentrations. Like these are not.
You said
It's not like
most
we're
organic.
scratching our heads. How can we form amino acids naturally? Like we're finding them naturally, pretty abundantly.
So you said most of the carbon in space is organic.
Well, yeah, I mean, organic means carbon containing molecule. So by definition, yes, but most of the carbon in the universe is found in like polycyclic or aromatic rings found in like these basically around clusters of ice and dust.
Okay, so CO2 looks like is the majority of carbon in space, and then organic carbon would be bound to like hydrogen atoms, which is less common in space, from what I'm
Yeah,
reading.
if
If you
you
have a
would
different
like for me to, I mean, I know that you really like Googling in the middle of debates, but if you would like for me to show
can't
you,
believe that
I could
statement,
Google the study where I could get you the 40% of carbon in the universe is contained in PACs. I could get you that number if you don't believe me. It's in a study on astrophotochemistry. I could go and try to track it down, but like I don't typically Google
Yeah,
things
that was
during.
just kind of a radical statement to me, so I was just kind of like, "Whoa, that's weird." But if it might be true, I don't know. But yeah. Anyway, so the last thing I wanted to kind of touch on is the protocell. You kind of mentioned a protocell. So, what do you think the smallest form of life would need in order to be a protocell? Because not many people will define what a protocell actually is. So, if you have one, that would be really important to me to hear. That'd be awesome.
Yeah, okay. So, I kind of like NASA's definition of life, which is basically just something that's capable of undergoing Darwinian evolution. Um, and so, I mean, it's a simplified definition. Nobody's got like a perfect definition of life that's universally agreed on. But I think as a simple definition, that's a pretty good one. And in order to have a system that's capable of undergoing Darwinian evolution, we already went through everything that was required. There are actually not just amyloid systems, but multiple chemical systems that kind of like can start to undergo, like they have the properties that would be able to undergo Darwinian evolution, so they start getting you on that trajectory of life. So, yeah, I mean, I don't know what you were saying, like if you want me to give like a minimal, I don't know, because I personally think that life is like there's a gradation, right? Like there's gray areas in between. It's not like all of a sudden, oh, now you have life and this isn't life. Like viruses kind of in that gray area, prions even like further down that gray area. Like there's all these kinds of molecules that have life-like properties. Um, and it's like, where do you draw that line of this definitely is and this definitely isn't? I mean, it's a little bit arbitrary. Like literally,
Yeah.
science cannot even
I
agree
think
on a
being able
definition
to
of life.
Yeah, I think being able to have like self-sustainability and like process energy that would be needed for these reactions, like eventually they got to start synthesizing their own amino acids because this nice little pool of amino acids, like I'm not sure
Mhm.
if you expect them to constantly be coming in this form, but they eventually like need to start forming their own to make their own proteins and start using those proteins to like replicate the genetic material, which we haven't even really gotten to. This is like we're covering such a small subset of what would be needed in the original life. Like we haven't even gotten to how DNA came about in our conversation. Like we're very at the beginning stages, and so yeah, these are all really important questions. Like, but I think that having like some like even if I was to just give it to you, like yeah, okay, we can have these like amino acids just like readily available and stable in early Earth, and they're next to these readily available stable RNAs that can all come together and form in the right chirality. And then we have these like amyloids that can then impose their position and their folding onto others and basically replicate other ones like it. Like then we're still not even close to life. Like um there's yeah, like it's just really sad like how far away we are from answering these fundamental questions. And like, even if we were to have amyloids, like, then what? Then, okay, so we have these amyloids that can then form other amyloids and they're diverse. Like, what would be the next steps in that to forming life?
So basically, the next step is to go from a system of heredity that's based on amino acid sequence to one that's based on nucleobase sequence, which I do think you almost get this really interesting sort of intermediate on their way there with that study that I had sent you about the amino acid and nucleobase chimera that was self-replicating, because they had a protein component and a nucleobase component to that. And the sort of structures that it was forming were stacking and they were replicating the sequence of the proteins, and they had, just as a secondary feature, they had a sequence of nucleobases, but the sequence of nucleobases was stacked and not hydrogen bonded like in DNA and RNA, or like
Mhm.
DNA. And so it's like it's not like they created this sort of DNA sequence or anything, but they did create a sequence of nucleobases that spontaneously formed, but the actual selection pressures were for the sequence of the protein and not the nucleobases. But you had both of them existing in a sequence. So I think that that is a very interesting intermediate that was formed in a lab where we can see this sort of self-replication of a sequence that then also has with it a secondary sequence of proto RNA type material, which I found like a sequence of nucleic acids. So I think that you have it's most likely that there was some sort of like a chimera, sort of like ribosomes are, of RNA and proteins. There's a population of these chimeras, right, where you have a sequence of being replicated of the protein, that eventually the superior method of information storage becomes not storage in amino acid sequence space, but in nucleobase sequence space. So that is the next transition to where you start to get the central dogma of biochemistry.
Right. So, I mean, the leaps you're making there are funny, but I mean, yeah, you have to have all these different systems in place basically for the first cell to be able to be sustaining and functional. And, another question I had was about the amyloids. Like, if they're just like imposing proteins to become just like themselves or, templating and replicating themselves, at what point would that stop? Because that seems like eventually that would actually be detrimental to the first cell. Whereas we would need basically these functional proteins to start coming about and to start having their own functions without being, affected by the amyloids that are present that normally lead to detrimental effects like in neurological conditions. So at what point will we move from this like, okay, this protein's behaving weirdly and making other proteins like, also behave weirdly or making these weird, unuseful like components potentially to like, okay, now we're actually getting some functional proteins like how would that transition happen? Would the amyloid stop forming? Because at some point that must have needed to happen.
Yeah, so again, this is the transition that you're talking about is using amyloids as your storage of information to using like DNA or RNA as your storage of information. And so I think that you did a great job of elucidating exactly why that change needs to happen because the sequence of amino acids is functionally relevant for catalytic activity. So it's not a very good information storage system. DNA, you don't necessarily need, like, I mean, you can have ribozymes and things, but like, it's a much better information, like, nucleic acid is a much better information storage system. So there's obviously there's optimal, it's more optimal to transition, but how that transition happened and why, I mean, we can see that there's a clear, like, advantage to making that transition. But in terms of how I would speculate that it would involve something like a proto tRNA. Because obviously what we're talking about is the evolution of the central dogma from, DNA to messenger RNA to proteins. tRNA is the main player there, like the ribosomes and the tRNA. So
Yeah.
I would speculate that again, you'd have this early population of protocells that might look a little bit like some sort of proto-ribosome, where you have a chimera between nucleic acids and proteins that's self-replicating, and you have to get these mediators. So, like, there's going to be a part where they start to break apart into sort of more subunits that can act as sort of enzymes, and like those sequencers are replicated and you basically have to then they're good at recruiting and binding with nucleobases. We've seen that they attract triplet codons. We've seen that these chimeras can replicate a sort of sequence of nucleobases, even if it's not, sequentially relevant for their function, they'd still do it. So there is that interaction. Somehow out of that interaction, essentially you have a mediator, like they are attracting these nucleobases. These nucleobases must then act as a mediator between the sequence of amyloids and a sequence of nucleic acids. So that mediator then is essentially evolving into tRNA. So Sutherland has done some really interesting research about
Mhm.
how tRNA came about and how the system actually makes the most sense as like to why tRNA is shaped the way it is and how it could have evolved that way. He specifically has a study on the structure of tRNA in this prebiotic setting that I find really compelling.
That's actually on I was researching tRNA recently. So do you think that there is a theory on how it could have formed and became this like translator system between two different codes
Yeah,
that weren't
so
really existing yet?
I think that that's absolutely the key that we need, but I don't think there's a theory of that now. But I do think that I'll send you Sutherland's paper about it because that's what I was reading. That was probably the most cutting edge thing that I've read on it was coming out of his lab, and that was sort of like not a complete theory, but it was like the first clues that are like suggesting about the formation of tRNA. Basically, it was really interesting.
I read about something where like the stereochemistry of the RNA could have been attracted to the amino acids and to the proteins, and that yeah, that makes sense. But you would have to eventually start having these form in the same exact conditions, right? Just like like the cell does, they'll form the RNA and they'll form the amino acids, and then they come together, right? But if they were they're forming in the same conditions, I feel like that would pose some issues on the cell. And
It's
I think this is why Sutherland didn't do them like in the same pot. There are a
so
couple different issues, like with the free phosphates being there, or
so
the
the
amount of magnesium that would have needed to be there for the tRNA versus like how much could have been around the RNA. And then also like the Maillard reactions from the amino acids and the sugars like ribose that can basically react and deplete the available ribose for RNA synthesis. So while he does have an explanation of stereochemistry, I think that wouldn't explain like how they both simultaneously form side by side, and then it wouldn't also explain like how the code came about and the translating system between these two codes that somehow arbitrarily came about just by accident.
So okay, so the um, sorry, oh man, I had something that I was trying to say that entire time, and then right when you stopped talking, it left my mind. So can you repeat the very first point that you made? That's what I wanted to respond to. Um,
Yeah, so the stereochemistry between the RNA and the amino acids, like basically we've seen them coexist, but have we formed them
oh,
from inorganic
right,
compounds
right.
in the
The
same?
same pot. That's what I. Sorry. Yes. Sorry. The whole time I was like, you're not. You don't have to form these in the same pot. That's what I was trying to make the point of. Is that what we're specifically talking about with amyloids or with hydrothermal vents, both of those systems are prone to compartmentalization. So you can have hydrophilic and hydrophobic pockets forming readily, just
In the
in the
hydrothermal vent rock? Is that what you're
yes,
saying?
so in the
Okay,
rocks of
so
hydrothermal vents, there's all of these sort of like the surface area is full of these little pockets where you can have very interesting micro environments forming based on just like what chemicals end up there, and you can have micro pH and micro environments in there. But you can have the same thing in amyloid fibrillar networks. These amyloids form these vast structures of fibril networks, and in them there are hydrophobic pockets to where you can have like unique chemistry, and they can sort of these amyloids are these primitive proteins act as really simple enzymes to catalyze reactions that wouldn't occur in the normal aqueous environment.
would they have wet dry cycles in the aggregates?
Not to my knowledge. No, the wet dry cycle would have to be something that occurs near the surface.
Yeah, that would probably pose a big problem.
Well,
Because
I don't see why, because like wet dry cycles are just like an alternative route at getting at some of the
for
same chemistry.
RNA
Like there's lots
synthesis,
of different approaches.
right? So like yeah. So like for RNA synthesis, they've shown like the need for these wet dry cycles, and that's kind of why Sutherland proposed some of these ponds in his experiment. He wasn't proposing hydrothermal vents, but so hypothetically, for the first proteins to come about, and then the first the first RNAs to come about, like to even get the first amyloid, those would have to happen. And you're saying like these sub pockets of a rock in next to a hydrothermal vent. Is that what you're saying?
No, that's not what I'm saying.
Okay, well then maybe you can explain. Sorry.
Okay, so like again, the amyloids, they can form an aqueous solution like just with volcanic gases acting as catalysts. In terms of the formation of RNA, there are different biochemical routes to form RNA, like the wet dry cycles on clay or whatever. That's one route that you can go by. You can also go through like enzymatically catalyzed reaction where like these early proteins can catalyze the formation of RNA from like naturally occurring nucleobases. So
So,
there's
but what
multiple
about that's what I
different ways.
mentioned? Because like the wet dry cycles would be needed in some of these cases. Sometimes you need the aqueous environment for things to come and react, but then if they were continued to be exposed to that aqueous environment, they would then be hydrolyzed. So would the like amyloids like prevent that from happening? Like, or
Yes.
would they have some sort of wet dry synthesis cycles and pH
So
microenvironments in the amyloid
you,
aggregates?
what I'm trying to say is you don't need wet dry cycles. Wet dry cycles are an alternative option, but they're not absolutely necessary. They're not a like they're one hypothesis for abiogenesis. They're not a necessary aspect of all hypotheses. So for like specifically amyloids can stabilize the formation of like RNA or nucleobases whenever they bind to them, or with lipids, they can preferentially stabilize these things and protect them from degradation via their interactions. But also, you did say that you were going to ask me like one question like 6 questions ago. I don't know if we're like, I don't know where we're
This is
at.
one question still. This is a conglomeration of one
Okay.
question of how life formed. Because yeah, I mean, I could honestly ask you questions all day, but I understand it's like I kind of feel bad because like you're kind of at a disadvantage because we haven't shown some of these processes to occur, and a lot of it's like hypothetical and appealing to possibility at this point. So yeah, it is kind of fun to hear like what people think could happen because in all these different reactions, you need all these different environments and pHs and temperatures and amount of water presence. So and then UV light, and then but you couldn't have UV light, like Sutherland's papers,
That's
like you need UV light for the RNA, but then you'd have to stop it at some point because it break it apart. So
yeah,
it's so funny to
that's
maybe
what
if
I'm
you
trying
have a concise theory, you should publish it because all these different sub environments that need to be there are just kind of hilarious.
Well, that's what I'm trying to been explain to you is that that's
Mhm.
not the case. There's not all these different sub environments that all need to be there. It sounds like you're just like mixing together a lot of different hypotheses for abiogenesis and saying that like something from this hypothesis needs to be there and something from this other hypothesis also needs to be there, and it's like no, those are different routes, different hypotheses. You can't like say, oh well, they're all true and they're all contradictory, so therefore it's impossible because they all need different environments. Like that is not a correct reading of the state of the literature.
So this is why I'm saying it's so important to start from scratch because we could see which ones contradict with one another. Like, in the formation of amino acids and then in the formation of the RNA, they have different experiments, in different conditions that they've shown need to be there. And then for protein synthesis and RNA synthesis. So this is like one of the reasons it's difficult for them to do it in one pot. And just looking at all the leading papers on abiogenesis, they'll invoke different reactions and they admit that. But it's funny because they add on to other experiments that have been done. They say, okay, well, we know amino acids can form because of this experiment, this experiment. Now we're going to do this experiment with different conditions to show some other product. So there's a reason why it's most likely not sequential because they have different environments that they need. They hyper tweak these experiments to work for their particular scenario that they're trying to demonstrate. But then again, that's what I'm saying. It's not really relevant because you need to come up with some storyline of how this happens in
Yeah,
somewhat similar conditions.
I'm trying to say that you're mistaken in thinking that all of these different environments are all required because these different papers illustrating very different aspects of abiogenesis are using them. That is not a valid conclusion to draw
Can you tell me
from
what I'm
the.
mistaken in particular?
What was that?
What can you give me an example of something that I've been mistaken
Yes.
on?
Yeah, I'm trying to say, like, when you're saying that, oh, well, over here, wet dry cycles are required for RNA synthesis, and therefore that means that wet dry cycles must be required for RNA synthesis in amyloid research or something. And, like, or it must be that there are wet dry cycles creating the RNA for, like, hydrothermal vent ideas. That is what you're wrong about. That is fallacious reasoning because those are different pathways entirely. The pathways of RNA production for hydrothermal vent models are going to be different than wet dry cycles. Like these are different ideas. Like you're basically abiogenesis is currently not one theory. There are currently multiple different competing hypotheses. You cannot say that all of these hypotheses are all true and all occurring at the same time. That's the fallacious reasoning. Because for you to say that it requires all these different sub-environments requires you to say that all these hypotheses are all occurring simultaneously, which is just not a correct reading of the science.
Yeah, so like for example, like I've seen the papers where like short RNA sequences can bind to the peptide amyloids, but have they formed these ribonucleic bonds in the presence of amyloids? Like, have they simultaneously formed those bonds, right? And but I know that they can stabilize one another. I know that they can have like some sort of stereochemistry and like stabilize once they're already formed, but it's the synthesis of the amino acids and the peptide bonds and the ribonucleic acid bonding, right? The RNA bonds of the nucleic acid. So things like that would definitely need some more like experimentation and demonstration. That's why it's kind of hard to get a concise theory, because they're adding on to previous experiments and they're using different conditions and different chemicals. So that's why I think a lot of these aren't really prebiotically relevant if you go read like the materials and methods of each of them.
Well, yeah, a lot of them are not trying to be prebiotically relevant because that's not the point of the experiment. Like, you have to go in with the experiment saying, why are they doing this? What is their goal? What are they trying to elucidate? And it's like not every single experiment is going to be trying to elucidate something that requires prebiotic starting material. Like, they're going to be interested in some other aspect that they're investigating. Like, it depends on the study itself. And like, yeah, there are other studies showing that like you can have RNA formation catalyzed in some sort of peptide RNA world in an aqueous environment that's not using wet and dry cycles. Like, there's all kinds of different abiogenesis experiments out there trying to figure out different ways to form RNA. It's not saying that like there's just one way that we know RNA had to have formed and it has to be wet and dry cycles. Like, that is not the state of the literature.
Right. Well, if we could show the formation of RNA, or if we could, show these nucleic acids being synthesized with their phosphate backbones, in the presence of other, amino acids already there and their formation, like, that would be really cool. But so if they're not being prebiotically relevant, however, I don't think that they should be used like as evidence of undirected abiogenesis rather than evidence, rather than like a suggestion of, hey, once it's already there, this could happen, which is kind of what they're doing. But I don't think you should use that as evidence for undirected synthesis of life on early Earth conditions.
Yeah, well, I don't really think that people are necessarily pointing to these studies as saying, "Oh, look, this is like evidence that abiogenesis happened this way." Like, that's not the point of the
I
research.
think they are
I
sometimes.
don't think so, Taylor. I think you're misreading it because the point of the research is to investigate what is chemically possible. You're trying to create primitive chemical systems and then play with them to figure out what they can do, what they're capable of. You're trying to learn more about the world. That's why you do science. You might have an ultimate goal of, hey, maybe if we could show if that this is how life could have arisen, but the goal of these experiments is not like what you're portraying them to be. Like, it's like any other field of science. Like, you said that you like worked in a biology lab or something, so you've done science, right? Like, you know that like when you're set out to do an experiment that you have a grant for, like, you are
Yeah.
going to be interested in one particular aspect. You have one very narrow field of like that you're like trying to solve, right?
But,
Like,
but people do use these as evidence and say, hey, this could indicate this happened. But, I just feel like if it's not prebiotically relevant, it shouldn't even be in the field of evidence for abiogenesis. That's just my
okay,
opinion. And I think,
okay,
yeah, I
that's
know
fine.
you disagree. It's okay. We can disagree on that, right? But
Yeah,
I disagree.
that's fine that you like feel that way, but like, is that an actually like reasonable expectation to have in the scientific field if you want to actually make progress? I don't think that it's very logistically feasible. I don't think any other field of science would do anything like that. Like, they're just not how any field of science works. Like, if we want to figure out, hey, can amyloids self-catalyze? Then we specifically construct an experiment to test whether or not, in principle, amyloids can do autocatalysis. It's like, oh, well, that experiment doesn't count because you didn't start from prebiotically relevant starting materials. Like, well, that's not what we were trying to figure out. That wasn't the point of the experiment. It's like, yeah, I just feel
Yeah.
like I feel like you're special
As long as you
pleading
don't present
or
that as evidence, we're good.
I think you're special pleading for origin of life research. Like, you expect a different scientific method out of origin of life research than any other field of science. Like, if we're just looking at the way that research is done in science generally, there's nothing different happening in origin of life versus any other field.
How am I special pleading to ask for them to replicate prebiotic Earth conditions in a claim that says life can form on prebiotic Earth?
Because like whenever we're investigating like a specific research question in science, right? Like if we want to like if we want to investigate like what is space fundamentally, right? Like a quantum space, right? Then like if we're going to pursue that kind of research question, then like we don't just start with, okay, well, let's try to replicate the conditions that created space. You don't just start out with that. And if you're trying to investigate like what space is made of fundamentally, then like you wouldn't you can investigate certain properties of it. You can say, oh well, what's the smallest amount of space that's meaningful? And then if you say, oh well, that question doesn't matter at all because you're not replicating the kinds of conditions that actually create space or where space originates from. Like, you know, even though you're trying to figure out where space originates from, that's what the answer to the question that you're investigating. The way that you're investigating that question is to investigate, well, what are the properties of space? Maybe there are some properties that can elucidate something more deeper about what it is fundamentally and where it comes from. It's like you start by investigating as many different characteristics and properties of it as you can. You don't just have to say, well, the only research that we should ever do to answer this question is just try to focus on replicating the conditions at the origin of space.
But if they claim that space can originate from some chemical reaction, and we have chemical reactions that we can replicate in the lab, that's not too unreasonable to ask for. Yeah.
Oh, yeah, but okay, so basically, my point is that this research of abiogenesis
I
is not
understand your point.
necessarily.
I get it. I get it.
Really,
I really
but I
do.
haven't made it yet. I haven't. I genuinely haven't made it yet. I the
just
point.
want to step in. We're about almost 2 hours in. Do you guys want to switch to Q&A at this point?
Yeah, we can. I'm gonna go turn my fan
There's
on or open the window because it's hot up in here.
Yeah, there's a bunch of people who want to ask you guys questions.
Oh, good. I'm glad we have a bunch of questions. Perfect. Let me go open this window for a second, and then I'll come right back. Is that okay?
The point that I was trying to make before the start of the Q&A was that the evidence for abiogenesis is not anything that we talked about tonight that I would point to. Like, I don't think that any of these experiments are necessarily evidence for abiogenesis. It's just evidence that primitive chemical systems can do some really interesting things that like might start to resemble life. But in terms of if you actually were to ask me what the evidence for abiogenesis is, I wouldn't bring up any of these studies. That's why I was disagreeing with Tayler and why I was saying that wasn't my point of saying that these studies are the evidence for abiogenesis. I think that the evidence for abiogenesis is the fact that we know that at one point the universe did not have life. We can look at the cosmic microwave background and see, hey, at one point the universe was entirely plasma, no life. Now there is life. So there's a gap right there. We know that something had to start life, either naturally or supernaturally. The evidence I would point to is the past track record of naturalism as saying, hey, if I'm a betting man and I'm putting money on whether or not I think a naturalistic explanation or a supernaturalistic explanation is more probable, based on the entire history of science, I would put money on the naturalistic explanation. That's my evidence for abiogenesis that I think is the actual evidence. None of these studies showing what chemicals are capable of doing. I just think that stuff is neat. That's saying, hey, well, like, look what's possible. But like, the actual evidence is like what we have in geology and physics and earth science.
But wouldn't that be like a hasty generalization where you're making like a claim and saying that, it can also apply to abiogenesis even if we don't actually see it applying? It's made based on like a small subset of like experiments or like the fact that other things have been proven naturalistically. So therefore we're gonna like generally say that yes, most likely this can be proven naturalistically, like appealing to like the future or something like that. Like I just don't see the logic in that reasoning.
So my logic is basically like when we look at the overall trajectory of history, all the like not all, but the vast majority of previous supernatural explanations have been replaced and debunked by naturalistic explanations with science. That's true for most things. There's a small number of things to which we still don't have a naturalistic explanation. But I would go ahead and pick with the winning, the trend line winner, which is naturalism. Like science is definitionally naturalistic. Like you can't have a supernatural hypothesis because then you're not doing science anymore. So I'm just going based on the successful track record of science. I'm saying, look, I'm just looking on history and I'm thinking, what's the more likely scenario. And based on the track record, I've got to go with one day we'll probably have a scientific explanation for abiogenesis just based on the previous success history.
But that's not positive evidence for abiogenesis, though.
But that's
That's
my
just
reason.
assuming.
Like
Okay,
that is
I'm just
that is
letting
the
you
reason
know.
why I think that abiogenesis is more likely, and I do think that that is evidence for it, insofar as evidence can be defined as a set of data which makes one conjecture more probable than others. I do think that the previous history of science and the successful track record of naturalism is data which makes it more likely for there to be naturalistic explanations for all
But
things,
there,
then it makes it like then the alternative conjecture that there's supernatural explanations for things, which is less likely under such a scenario.
but under their like naturalistic explanations for things like, you know, the universe, like we've gotten to a point where the only thing that we see is like 5% of what's actually there, and now like most of the universe is this like unknown like dark matter and dark energy. So I don't think that they have a very good record if most of everything that exists we can't even observe or
Yeah, well,
test.
in terms of summarizing the number of phenomenon that used to have a supernaturalistic explanation, I mean, everything from rain, lightning, thunder, wind, birth, death, plagues, famines. I could go on all night at the sheer number of phenomenon. If you just want to go based on the total energy density of the universe, that's a super weird metric to use. I'm just going
Not
by,
energy
look,
density,
the
everything.
denominator for my number is the total number of claims of all phenomenon. The denominator for your number is the total energy density of the universe. That's how you're getting that
Um,
5%. I think that's a
that's not
super,
the same.
super weird metric to use, and I think mine makes a lot more sense.
Okay, well, I was just saying that, you know, naturalism has gotten us to a point where we only understand and can work with 5% of the universe.
Oh,
And so
5% of
it's
the total
safe to
energy density of the universe, though. That's why I'm saying it's a
say
weird
dark
percentage.
matter and dark energy, not
Should
just.
probably go one at a time, guys.
Yeah, I'm just saying, like,
I was just
Taylor
gonna
is
say like
saying that we only understand 5% of the total energy density of the universe, which is a dumb metric that nobody would want to use ever. Like, the actual metric by which we should use is how much
Should
of the
probably
total,
avoid the ad homs.
how
yeah,
much
I
of
wasn't
the
saying that was my metric either. I was just saying it's
You've repeated
ironic
it two
how
times as the metric that you want to use. I'm going based on your words. The actual metric that anyone should use is the total number of phenomena known about versus the total number of phenomena with naturalistic explanations. That's what we should be talking about if we want to have a good faith discussion.
All right, we're getting off topic here. Graylin, if you think that the Q&A is the end, we're only just beginning.